cluster competition with some prizes, so I hope everyone sticks around for that. Just as a reminder, HP is doing a little giveaway too, so right there in the back, throw in your card. Maybe you can win that little server that's up on top. They're going to announce that around lunchtime. And then right there by the HPC Advisory Council booth in that, box, go ahead and throw in some more information so you guys can win possibly a prize at the very end of the workshop. So with no further ado, I'd like to introduce Goldi Misra from C-DAC as the keynote speaker of today's workshop day.
Thanks, Brian. Good morning, everybody. Welcome to the HPC Advisory Council workshop. I thank Gillard and Brian for inviting me for this HPC Advisory Council workshop, and also would like to mention a good work is being done by the management of CSCS in organizing such workshops and hosting such workshops. I'll get on to the presentation. This is to cover the C-DAC HPC activities and the experiences which we have had on accelerators. So broadly, C-DAC activities are into various thematic areas. So research and development areas which include high performance computing, grid computing, and lately cloud computing. Multilingual computing and heritage computing. These are various, since India is a vast country with many languages. So this plays a very key role in our country, and various research and development has taken place for solutions in multilingual. Then health informatics is another key sector wherein we are developing our own solutions as well as deploying solutions pan-India for decision support. Then we have our own HIS, hospital information system, telemedicine system, and so on. So software technologies which includes free open source software. So in line with the Government of India Ministry initiatives on the promotion of free open source software, the various initiatives around free open source software in e-governance and for ICT for the masses and geomatics, etc. have taken place. On the professional electronics, including VLSI and the embedded systems, there is work going on by one of our centers in digital broadband and wireless systems, network technologies, power electronics, real-time systems, VLSI design, and agri-based electronics or strategic electronics. Cyber security and cyber forensics is another area wherein C-DAC has been working. We have developed our own cyber check suite, cyber security tools and technologies, and we frequently conduct research and training for various organizations in this area. So across all these areas, education and training forms an important component of C-DAC activities. So these are some of the products across all the thematic areas. Sorry. So in HPC grid, multilingual computing, professional electronics, software technologies, cyber security, and health informatics. So these are indigenously developed products being deployed at various locations. So let's get to HPC activities. Spectrum of HPC activities. So you see technologies is what we are into actually. Building of systems and national facilities, because we have our own set of facilities which we help users across India and outside, wherein they can access and solve their problems. Applications is one key area wherein we concentrate on porting of various applications, running these applications on facilities and systems, and developing solutions wherein we can help HPC reach masses in a big way and make a difference to society. And trainings is trying to address the grassroots or to inculcate a HPC environment and a culture across all the science as well as the engineering domains. So Param 8000, the first Param in way back 1990, is based on C-DAC's indigenous technologies on the computers. Then Param 9000, 10,000. Then we have Param Padma. The last one was Param Yuva, which is a 54 teraflop machine with a 200 terabyte storage, which is being upgraded, in the process of being upgraded now. So these are the various indigenous Param national facilities of C-DAC. So this is a slide giving a snapshot of the Indian supercomputing scenario. So initially in 1990, the first supercomputer was done by C-DAC, that is the Param 8000. In 1990 to 2000, a lot of parallel initiatives by BARC, that is in the research of nuclear, DRDO, we have flow solver. So this is about a decade of effort, parallel effort has been taken place for specific applications. So supercomputing for specific applications was the theme. Now several HPC facilities have been set up at C-DAC, ISC Bangalore, BARC, NAL, CMAX, DRDO and NCMRWF. These facilities are more of facilities which take care of their own applications and very much centric to running their own applications and solving their own problems, as well as into production grade environments. Then C-DAC's Param Padma was ranked 171 in the top 500 in 2002. Then CRL's ECA was 4th in the top 500, that is in 2007, wherein 9 terascale systems from India were in the top 500. We have our own Param Yuva, which was launched, which has C-DAC's own ParamNet 3 interconnect switch as well as cards and InfiniBand both, in the which ranked 68 in the top 500 in 2008. So just to give a comparison, only 4 systems were from India were in the top 500 against 41 from China. So India's best was ranking 47 in the top 500 in 2010. So lately, Indian government has taken a big initiative and in supercomputing. So HPC. So these are some of the snapshots of the national facilities at C-DAC. This was the Param 10,000 system in 1998. In 2003 at C-DAC Bangalore, that is CTSF, C-DAC's terascale supercomputing facility. This was Param Padma. This is the National Param Supercomputing Facility, the 54 teraflop Param Yuva. That's at Pune. So mission-wise, we've been working on various, first mission was building of the machine, and thereon we have been working. So the important part is that Grid Garuda, so by 2008, C-DAC has established Grid Garuda initiative. So it's a connectivity of various systems across 45 institutions and 17 cities. So this is what is culminating into the National Knowledge Network and the cloud recently, which will be. So various application stacks on structural engineering, bioinformatics, so FRP smart structures, fracture mechanics. So on bioinformatics, we have MEME, protein folding. On seismic modeling, seismic inversion, pre-stack migration, 2D and 3D models. So on evolutionary computing, we have various protein structures and so on. And weather forecasting, we have WRF and real-time weather forecast systems. So on the CFD, we are working safe on the launch vehicle and electromagnetics. These are some of the applications. There are many other applications wherein work is going on using the national facilities. So this is the Garuda I mentioned. This is the National Grid Initiative, wherein connectivity and even grid enablement of various applications of users across these labs has taken place. So most of these users have been able to use resources or to even distribute their application across various resources and get results on a very fast. So this is across 45 institutions across 17 cities. So indigenous cluster ecosystem tools is we continuously build on indigenous tools which will help or which will even proliferate HPC across the entire ecosystem. So InClus is one of the tools, is HPC cluster building toolkit. So this is to be inaugurated soon. It is in the last stage of production. So we have CREM HPC resource management engine. So we have ONAMA HPC package for academic institutions, and we've also on the closure of a parallel file system. So InClus, this is a web-based and a web and desktop GUI-based. It's a cluster toolkit which works on most of these OSs. It has got scheduler and resource manager, policy-based accounting, high availability support. So most of these features are are industry grade features which can be used for larger scale installations too. So this is soon to be launched and will be deployed at one of the collaborator or customer sites. We have CREM. This is the C-DAC's HPC resource management engine. So this addresses the challenge of efficient and easy usage as well as management of resources of HPC systems. So usually the problem which we faced at a lot of collaborator sites were our domain experts were never computational scientists. They were experts in their own domain. So to make life easy for them to use supercomputers, this tool has been developed by our people. So this is a portal which can help for end user job submission management. It's a monitoring tool which works well with industry schedulers such as STOC, OpenPBS, SunGrid Engine, Mob, Load Leveler. So we have timely email notification regarding job status, personalized job list, as well as job status information. Then secure credential specific access on web through HTTPS. It allows users to configure their execution environment through compilers and library selection, scheduling parameters, etc. And scientific and research application portals. So it depends on various labs. Now most of the labs are very specific to some activities. For example, we have a lab which is more relevant to weather prediction. So we can have this CREM very specific to weather prediction. So weather related models can be a part of this portal and they can use this. It will become much simpler vis-a-vis compared to a university environment wherein a lot of various domain scientists are working, trying to use the HPC facility. There we can have right from bioinformatics, we have evolutionary computing, we have seismic, or we have any of the physics, chemistry, biology related applications. So most of the science related applications can be integrated onto this portal. So on the ONAMA, this is C-DAC's initiative. What we've observed that HPC, the proliferation of HPC in engineering colleges, so that engineering institutes per se, India has a large number of engineering institutes and the curriculum has not taken care of HPC as much, so we are trying to inculcate the culture of HPC in the syllabus. So this is a tool which has been created. It's an integrated package of various open source tools for all engineering institutes. So it's so right from computer science, mechanical, electronics, communication, electrical, civil, chemical engineering, and this is more of providing a low-cost cluster solution to these engineering institutes, which can serve as a proof of concept, and they can use or they can get an idea of parallel computing. So all across many of these engineering colleges, we have tens of thousands of such engineering colleges in India, wherein we are trying to have this solution, which is a low-cost solution, wherein with small data sets they can learn and get an idea of parallel programming. So we are trying to include NVIDIA, CUDA applications also. So this gives a good exposure to engineering college students as well as engineering college faculty to even parallelize various applications and to learn parallel programming, MPI, OpenMP, or to CUDAize various applications. So this is going well and it has got a good response, and we are also looking at bridging the gap of HPC users and trying to address the grassroots level. So whenever we have an engineer come out of the engineering college after completion, he would be HPC ready and can be part of any of the domains. So trainings and workshops are one of the very critical areas wherein we stress a lot. So parallel computing, multi-core, many core. So system administration and management, network security and audits. So this is essentially a part of any large data center or a HPC environment or a ecosystem. Storage management technologies, which is the next, it's going to make a big change, because as in when we compute more, so more of amount gets generated of data. So storage technologies and efficient management of storage or efficient management of data is becoming a critical area. Facility operations management and maintenance, GPU-based programming, HPC user symposiums. So this is symposiums which we hold very frequently within the country to promote the use of high performance computing, in various domains. So experts from various domains who are already using HPC for a great amount of time come and interact with users. These symposiums take place every quarter in various locations across the country. We have also come up with a C-DAC certified HPC professional program. Since we have been in high performance computing and supercomputing for more than 2 decades, we have come up with this certification program. It's a pro-metric program wherein people can just log in and can get certified on HPC. So broadly, the syllabus is distributed into 3 parts. That is the HPC fundamentals or the basics. That is about 1/3. And then we have system administration and understanding of the system per se. That is the next 1/3. And the last one is parallel programming, so actual parallel programming skills. So this is also a good initiative which is moving, and this certification helps people to have or to identify people who are the candidates who are HPC ready, and it's an industry benchmark which we are trying to create so that it becomes easy for recruiting or even for the collaborative activities in this area. So technology fallouts. So we have come up with indigenous capability in engineering and managing of large supercomputing systems and national supercomputing facilities over the period. Then hardware and software skills in designing system area network. So right on the chip PCB system design skills for our own interconnect, that is the Paramnet 3, as well as our own RCS. Then we have networking stack and system software, which is the ecosystem around our own indigenous hardware products. So we do all this prototyping, validation, certification, benchmarking, and training. So all this is indigenous activities. So hardware and software skills in designing RC accelerators. So RC hardware having up to 12 million logic gates for computing with different host interfaces. And porting of algorithms and applications as onto these hardware circuits to achieve a better speed up. Then software ecosystem design for various operating systems. So porting and scaling applications on large clusters is one of the activities which so this is primarily more of open source, and several collaborative projects in science and engineering research. So we are trying to increase the HPC user community, and a lot of publications are also coming around. So C-DAC is one of the beta sites for Intel Mike architecture. So we've been working on Mike for about 9 to 10 months by now. So we are working on the KNF, so Night Spheric coprocessor card. So about 1.2 gigahertz, about up to 32 cores, 2 GB DDR, 4 threads per core, and 300 watt TDP, and it's on a 45 nanometer process. So we have the Mike platform software stack 1.0 and 2.0. Development tools include Fortran C++ compilers, Intel MPI OpenMP, Intel MKL, IPP, TBB, ARB, Silk Plus, support for Eclipse, IDE, and OpenCL support is expected in the future. So the motivation behind using this is trying to port a lot of applications onto Mike card and just have an idea of how easy it is, and how because we have a lot of different groups working on various domains. So for us to have a lot of applications ported onto this and even optimized is much simpler. So we are expecting the Knight's Corner, which is the fully expected commercial product out of Intel on the many core side. So this is expected to be more than 50 cores per chip and a 22 nanometer process size, close to a teraflop on a chip. So this is, we expect that the larger systems in the near future will have more and more cores on a chip, and programming such chips will become more critical and shall be a winning factor down the line. So these are some of the OpenMP enabled applications which we had ported initially when we had the OpenMP stack. So on mathematical algorithms, Mandelbrot set was an example of simple mathematical definition leading to complex behavior. Then molecular dynamics, MD OpenMP. Oceanography is the tsunami N2 model. So this is a numerical simulation program with the linear theory in deep sea and shallow water theory in shallow sea, and on land with constant grid length in the whole region. So astrophysics CAM, so code for anisotropies in the microwave background, so computes cosmic microwave background spectra given a set of input cosmological parameters. So these are the various applications on OpenMP which we had done onto the mic platform. So these are some of the broad observations. We've done quite a bit on the MPI front also. However, that is under NDA right now. So activity is ongoing, and we expect to port all those MPI based applications onto KNC very soon and get an idea of how it's responding. So broad observations on the mic front are linear scalability and results are quite encouraging. It's based on very familiar x86 architecture, and it's run on the existing standard programming tools and methods. So minimal porting efforts were required. So no reprogramming for native compilation and execution. So directive based offloading, and availability of tools, so that is the profilers, debugging and monitoring, etc. were very easy. So we intend to work on the KNC to get an exact idea of performance and scalability, because right now we've been porting a huge number of codes, but we also want to extract the best possible performance out of it, so which can be done on a fully commercial product. Application accelerators is just to give you an idea of long-term viability of the technology. So since technology is changing at a very fast pace, so that's a challenge. Many technology providers do not stay in business for long, so we have a lot of people, accelerator guys coming in and are not able to sustain due to the business numbers. So application development methodology and tools, they differ substantially from conventional multi-core programming. So it's more of vendor dependent, and applications can be tuned to a good performance since it can go into whatever depth possible up to the hardware level. Then require a deep study of the underlying hardware architecture to achieve a very good performance, and codes are platform dependent. So emerging standards are coming around, so OpenCL for many core architectures. So GPUs is one, and OpenFPGA efforts for RC are also emerging. So these are some of the facts around application accelerators. So we have developed our own RC accelerator at C-DAC. So this is a second and third generation reconfigurable computing platform. So this is the card. We have our own Varada software stack which has been developed around it. If you look, this is the RC hardware, the kernel agent, the RC library, the math library, the compilers, and the application or the algorithm. So it uses RC hardware with state-of-the-art FPGAs. So RC hardware has up to 12 million logic gates for computing with different host interfaces. So these are the avatars are named, these are the hardware routines or the libraries which we have developed around the RC. We have Varada, which is APIs in the kernel agent, which has Linux support, which we have mentioned. This is again in-house developed. This is an eco-friendly HPC solution. So RC is an interesting paradigm which refers to a logic chip that can change its physical circuitry on the fly and accelerate applications by targeting the algorithms into programmable hardware. So scientific, if you look at, we start PCB design and assembly, the hardware library design, so this is avatars which we have named, the system software design, the digital systems design, and this is how we complete the entire C-DAC RC. So there is a huge amount of effort which goes in around building a custom built accelerator because it involves a lot of components, and lastly the biggest area has to be scientific applications. So even after the entire ecosystem is done, a lot of effort goes into the scientific applications or porting or getting algorithms or porting applications onto the RCS. So one of the enabling technologies, so as mentioned, is FPGA. So putting FPGAs on add-on cards or motherboards allow FPGAs to serve as a compute-intensive coprocessor. So FPGAs can be configured or reconfigured over and over again to perform multitude of operations. This enables application-specific or dynamically programmable hardware accelerators. So multiple functions can be called on. So we call function A onto the RC, or RC function B can be called on onto the card, and that is how we can move ahead. So performance of RC in our own param UVA. So the application selected was a Smith-Waterman sequence search for a protein database. So this is about 256 cores, so 16 nodes of HP DL580G5 quad-core quad-socket Xeon 2.93 gigahertz was the base system. So 16 nodes, so that is about 256 cores. So if you look at, we had a query that is, this has taken about 2 hours, 18 minutes and 31 seconds, and with RC on the same set. So what we are trying to, we are not comparing hardware with RC cards, we are trying to say how the same hardware and we have just added RCs and got a speed up of the same query on the Smith-Waterman. So we can say broadly it's close to 100%. It varies vastly with different kind of applications. So this is one of the slides picked up from various sources, Intel, IBM, Xilinx and Altera. So as the year on year, if you see the frequency scale up, we're comparing between a FPGA as well as a GPU. So if you see the scale up on a FPGA front is not as much, whereas on the CPU it has gone quite ahead. So in its C-DAC with its expertise in RC is capable of providing accelerated solutions in the wide area of scientific and engineering areas. So these are broadly the areas wherein we are working with various collaborators. Doing this on our own is an impossible task. We need to collaborate with a lot of people, wherein we are doing a lot of collaborative work for porting and running of applications onto the RC. So scientific and engineering applications in the area of fracture mechanics, radio astronomy, bioinformatics have been ported and significant acceleration has been observed. These speedups were further increased by many folds based on the configuration and applications. So this was the example which I gave some time back. C-DAC has also developed its own fracture mechanics custom code, which is having double precision Cholexy factorization and forward-backward substitution steps, which has been ported successfully, and we have got a 16x speed up. So very high-speed data acquisition and signal processing solutions are designed for the VLBI and power spectrum. Experimentation in radio astronomy has replaced a sizable computing cluster. So since the amount of output is expected is the fixed, so we don't need to talk of having a large cluster. We can have RC on a smaller version of a cluster. Double precision matrix multiplication has been implemented on RC, and it has performed better than the standard math library. In addition to that, we are working on some cryptographic codes on RCS, which is going fine. So the future is parallel computing, be it hardcore or reconfigurable. So evolution of RC logic design with more traditional computing paradigm has to take place. So when we are talking of RC cards on machines or servers, so how it works as a unit, single unit, it has to evolve in a much better manner. So development of more efficient cache replacement policy for FPGA configurations has to take place. That will help in a very good boost up or a significant help. So FPGAs which HPC which act as a solution to scaling challenges brought by microprocessors. So power consumed as well as clock frequencies are the two critical differentiators. So power consumption is very, very low of such FPGA cards. And since the CPU, obviously since clock frequencies are lower, so we can, so mapping compute intensive algorithms directly onto FPGA hardware. So whatever part of our algorithm is more compute intensive has to be just mapped onto the RC, and it has to be very tightly coupled to a conventional CPU throughout the high speed IO bus, and complete applications can be accelerated by orders of magnitude over conventional CPU applications. So, and development of runtime debugging of multi-platform enabled code has to take place. So that is another, because when we are talking of multiple applications run in runtime, so that has to move at a faster pace. So GPUs. So these are just a snapshot from NVIDIA. So these are the graphics solutions, so which has already been discussed and shall also be addressed by my by people from NVIDIA. So this is a good number to look at. So double precision, peak performance GFLOPS. So 512 cores. So this is with Kepler, and this is a Fermi architecture, and we expect a lot more advancements in the traditional NVIDIA GPUs. So these are various 512 cores, 448, and so these are the workstation based cards, and these are the servers and blades from NVIDIA. So this would be a very critical line to look at in terms of large scale or large scale peta and exa systems. So if you're talking of 2 to 3x faster GPUs every 2 years is what NVIDIA, so double precision gigaflops per year. So if you look at, we have Fermi 2010, Kepler is already there in place. So this is Kepler and Maxwell. We are expecting a great jump by 2014 in terms of the DP numbers. So, and a lot of effort going on by a lot of programmers to port various applications onto GPUs. So, but again, when we look at this product would be very critical for exascale systems, because if at all we are able to get to a very high DP per watt. If you look at 20 megawatt and as a ballpark figure for exaflop, so there we are looking at a much higher DP, so maybe 50 and beyond per watt. So if we talk of 50 gigaflops per watt, could be the magical number in terms of getting performance. So worldwide, this is another slide from NVIDIA. So worldwide GPU supercomputing momentum which is moving. So this is the Fermi, which is Tesla 20 series. So if you look at the number of GPU accelerated systems on top 500 is close to 40. So we expect a much more, a lot of activity to happen around NVIDIA GPUs too. So just to give you 3 ways to accelerate any application. So it's the libraries, directives, and the programming languages. So this can be fine-tuned to any extent, so you can obviously expect maximum performance, and the easiest approach for 2x to 10x acceleration. So this is out of a couple of years or more effort of so many users on NVIDIA GPUs. So GPU direct technology is coming, which also helps for accelerated communication with network and storage devices using InfiniBand, peer-to-peer transfers between GPUs, peer-to-peer memory access, and GPU direct, which can be very helpful for video-based applications. So PGI CUDA x86 now available for CPUs and GPUs. So single CUDA CC++ code base. So this is a major help. So NVIDIA CC++ compiler takes care of the GPU part, and the CUDA x86 compiler CC++ support takes care of the CPU part. So this is integrated, and it helps for having a heterogeneous or a hybrid programming of. So at C-DAC, we have the following cards. And this is the broad specifications of these cards. So in bioinformatics, we worked on GPU Hammer, which does frequent protein sequence alignment using profile of HMMs. And Mr. Bayes, so Bayesian interface for phylogenetic and evolutionary models. So CUDA Blast MP, CUDA Meme has been run. On weather, we have done WSM, so it's a WRF single moment 5 cloud microphysics module. So beyond that, also some applications have been worked, which is optimization is going on, and other applications wherein NVIDIA has also given us good support in porting and running on them. So broad observations are strong scalability of certain codes on multiple cards. So when the card number is larger, we found a good scalability. And obviously, since large number of users joining in on the GPU front, we could get comparative results also. Availability of numerous applications explicitly enabled with CUDA. So if you look at a huge set of applications as being running with CUDA already, and significant reprogramming efforts with CUDA for maximum performance. So if we need to get or extract maximum performance out of the entire thing, there is a significant reprogramming effort involved, and new and improved developer tools which have come up lately. So conclusion is having good experience on all the three kinds of architectures. So if we look at our own RC, we have also worked on mic and NVIDIA GPUs. So these are the broad aspects which are important. One is the programming complexity. So it depends on what application, what is the CPU or the core count, and what a user requires actually. It's not just talking of a custom fit solution for each and every problem. So if we are talking of a specific application and we can have that application, or that application has proved to work well on a particular platform, on any of these, we can look at if the scalability of codes is very high. So we'll have to look at cards or accelerators or architectures which have a longer roadmap and which are being supported by a wider community, and which can fit into or can form core building blocks of large scale, extreme scale systems. So library and tools availability, that is a big challenge, because getting all these things moving on an indigenous basis is virtually impossible for since the technology refresh is very high. So getting a lot of things on library and tools is another thing. So whatever solutions which we are working with should have a good availability of the library and good management or tools which can support the entire ecosystem. Then power versus performance is, since power has been a big challenge for the large systems as well as even small systems, since the HPC culture is moving and changing at a very rapid pace, people adopting to a lot of clusters and a lot of machines coming in, power is going to be a big problem. So getting a stipulated performance in the least possible power envelope is another challenge which has to be looked at, and that should be given due consideration. So flexibility versus accessibility, so it's both. So flexibility, so the way we can have multiple applications, if at all a facility has multiple applications or various other domains the facility is handling, so a lot of flexibility should be there for addressing application codes from various domains. So the system or this entire facility should be flexible in terms of your cores and accelerator availability, and it should be very easily accessible as well as programmable for any of the users, and the speed up. So what speed up do we get after investing what? So that is another point of concern. So we expect that accelerators will play a very important role. So from being a coprocessor card, it would also move on to the main board and provide application specific speed ups and provide a great help in terms of running applications and solving problems. So that is what is we are trying to look at. So these were some of the references wherein we have gone through. So with this, I would like to thank you all, and if you have any other questions. Thank you.